hold on, I've got some people coming into the class. Thank you. Yeah, so now it's recording. So a block is released from rest at point A as shown at a height of 8 meters. If the diameter of the loop is 2 meters, how fast is the block moving at point B? All right. So as always, the first thing that you want to do with these problems is you want to gather all the information that you have about the problem, right? So you want to put it all in such a way that it makes sense. So let's go with, let's go with here at the top, right? It's released from rest. The block is released from rest. So here at the top, my initial velocity is going to be 0. At a point A above, at a height, so at this height, my initial y is going to be 8.00 meters. Okay. If the diameter of the loop is 2 meters, how fast is the block moving at point B? So over here, if the diameter is 2 meters, that means that the distance from this point down here to B is 2 meters. So that gives me a height here of 2 meters. So my final y is 2.0 meters. And I want to find my final velocity like that. You'll notice here that they don't give the mass. All right, where's the mass? So don't. Okay, so no mass. What's going on? All right, so let's go ahead and let's set up our equations. And you'll see that as long as we're not dealing with a spring, we don't need to worry about them giving us mass. We don't need to worry about them giving us mass. So I'm given velocity and I'm given a change in position. All right. So if I'm given those two things in the y direction specifically, so I can use my conservation of energy. I can find kinetic energy and I can find my potential energy. So let's set this up. My Ki plus Ui is going to equal to my final kinetic energy plus my final potential energy. Okay. So Ki, we're always going to put that in mv squared, mv naught squared. My potential energy, I don't have a spring, so I don't have to worry about that equation, but I do have a change in y, so I'm going to put mgy naught. And on the right-hand side, again, I'm going to have a final velocity. I've got it on the left. I'm going to go ahead and put it on the right. Same for my potential energy, right? So that's what I need to use. Now, it didn't give us a mass, but every single term here has mass in it. So I can divide mass out completely. So I can get rid of that, it's all going to go to 1. So I end up with a 1/2 v squared, v naught squared, plus gy naught equal to 1/2 v squared plus gy. I kind of want to rearrange this just for fun so you guys can see something. Let's multiply everything by 2. Yeah, let's do that. Let's multiply everything by 2. So we're going to end up with a v naught squared plus 2 gy naught equal to v squared plus 2 gy. I'm going to move the velocities. I'm going to solve for v squared, so I'm going to end up with a v squared equal to a v naught squared plus 2 gy naught minus 2 gy. And then I'm going to have v squared equal to v naught squared plus 2g. I'm going to pull out the 2g from both of those, and I'm going to end up with a y naught minus y. So did I do that right? It's minus 2gy. Yeah. Right, so it looks a little bit somewhat familiar there, right? It almost looks like a kinematic equation. These should be switched. It should be y minus y naught, but still, we can pull out one of our kinematic equations from our energy equation. So just a little bit of an interesting thing to point out there. So I'm going to go ahead and substitute in my values. I'm solving for v squared, so it's going to be v squared equal to, this was 0 plus 2 times 9.8, 81, times y naught was 8 meters, and y was 2 meters. And in fact, if I pull this out, then I have a negative 2g y minus y naught. So just to show this, because I think this is interesting. Y naught squared, and then I pull out minus 2g, then I have a y minus y naught. And that's our kinematic equation there. And if I pull out that negative. So, cool. That doesn't mean, by the way, that you can use that for these problems. I'm just pointing out that we can derive our kinematic equations from our energy equations, okay? This is going to give us, I'll let you guys fill in the math in between there. That's going to give us a 10.8 meters, about a 10.8. You might see some difference there because I think I calculated it last. No, I think I did it right. Yeah. That's going to be a 117.72. So taking the square root, you should get 10.8 or something close to it meters per second. Sometimes I forget to put in that one when I'm 9.8. I just put in 9.8 for the G. So if your values are a little bit different from that, that's the reason. So don't think you're doing something wrong with your calculations or anything. I just sometimes forget to add in that one when I'm doing the calculation for these problems. All right. Okay. So last thing for energy is to talk about the escape velocity. Okay, and just like everything else we've done for this little section, it's got to do with our energy. Okay, so we're going to use the conservation of energy. Okay, and so we're going to consider that we have a rocket. All right, so consider a rocket with some mass m and initial velocity v naught, right, on the surface of the planet. Could be Earth, could be Mars, could be Mercury, whatever, some planet. Okay.
The planet would matter considering it would change the gravity.
Yeah, but we're not there yet. The rocket, the rocket comes to rest. Sorry, I couldn't read my handwriting. The rocket comes to rest when it's very far away. From the planet. right? So that just means it stops, right? It stops at some point really far away. So let's draw this out. So we have a planet, we have some planet. We don't know what planet it is, and you'll see it. You're right. It's going to depend on what planet you're on, but you'll see why um, we can use any planet here because we're not going to use gravity. We're not going to use 9.81. So some planet, we have some planet, and the planet, of course, the planet's going to have some mass m. We'll use a capital M for the planet because it's a big planet. And then we're going to have a rocket ship. And I usually just draw a triangle here. We have this rocket ship on the surface of the planet with some mass little m. Okay. And it's got some initial velocity. We don't know what that is, v naught. Okay, maybe it's standing still. It usually is. All right. And then it lifts off, goes up into the atmosphere and beyond. It ends up way over here somewhere up in the sky, and it stops, right? So we end up with a final velocity of v equal to 0. Okay. None of the other things change about the mass of the planet, so we still got this radius r, we still got big M, and we still got some mass little m here. Okay. What we do have is a change in this distance from the center of the Earth to where the rocket is. All right, that's r. And I think that's it. That's all we know, right? Yeah. Okay. So I'm going to use my energy equations. I'm going to add my initial kinetic energy plus my initial potential energy, my final kinetic energy plus my initial potential energy, my final potential energy. Right? I'm going to have, it's given some initial velocity, so I've got 1/2 mv naught squared. And then my potential energy, I'm not going to use mgy. I'm going to use the equation we originally got, the gravitational potential energy. So there's your gravity, but it's not using g. It's using the little g. It's using big G. It's using the gravitational constant times m times little m divided by r. And of course, I'll put all the same things over on the other side. I have 1/2 mv squared. That's a final velocity. Minus, and the minus comes from it being it's going down. Okay, the well, that's the equation, right? Potential energy equation up here. It's a negative. Yeah. So yeah, UG is negative GMM over R. Actually, right. It's a capital R here because the ship is an R away from the center of the Earth, right? It's that much distance away. So it's capital R here. Over here, it's going to be GMM over the little r because it's the total distance from the center of the Earth to wherever, or the planet, I shouldn't say Earth, the planet to the ship, right, to the rocket. Okay, this term, our final velocity is 0, so this term is going to go to 0. So let's rewrite this. We have 1/2 mv naught squared minus GMM over capital R equal to negative GMM over little r. All right, but little r is going to be much, much bigger than big R because it's really far away. All right, so I wasn't able to draw it very far away because I've only got a limited space, but it's really far away. That's what it says in the problem, right? It's very far away. So little r is going to be much, much bigger than big R. Um, so the bigger this is, it's going to get closer and closer to zero. So this one is going to approach zero, and so we can just say it's zero. It's going to go away. So that's going to go away too. And so we're going to end up with a 1/2 mv naught squared minus gmm over r, which is about equal to zero, because it's not going to be exactly zero, right? But it's going to be about zero. We can assume it's zero. So I'm going to skip some of the, oh no, it's not that much. I was going to skip some of the stuff, but we need to solve whatever for v, right? For v naught specifically. And so we're going to end up with a 1/2 m v naught squared equal to a g mm over big R. Multiply both sides by 2, we'll end up with an m v naught squared equal to a g mm 2 gmm over R. We've got an m on both sides, a little m, so those will go away. And so we'll end up with a v, and this is going to be called the escape velocity, actually, equal to the square root of 2gm over R. Okay. So you'll see there that we're not using 9.81. We're using the gravitational constant, the universal gravitational constant. We're using the mass of the planet. That's why it's going to be generalized to any planet. And we're using the radius of that planet. So generalized to any planet. All right. Right, and we call this the escape velocity. So this is the velocity we have to achieve to escape a planet. That was weird. Gravitational field of some planet. Okay. Yeah, I don't know what else to say about that. We just stick those in. There is a way to, what was the problem? Hold on, give me a second so I can. There's a problem on the exam, that one of the problems on the exam that you might encounter, that deals with, I can't remember what exactly it said, so I'm looking it up real quick. Where you have to kind of you have to look at look at this equation, and you have to look at the potential equation and what we know about 9.81 about the acceleration due to gravity, to solve the escape velocity for leaving some other body. All right, so it doesn't give you the what was it? It was like the mass. It doesn't give you the mass or something, but it does give you, like, it gives you the radius, and you have to figure out what the escape velocity is without having been given the mass of the planet. All right, so just be aware. You need to be familiar with this equation for that. In case you get that question, it's not a guarantee you'll get that question, but it's one of those conceptual things I don't want to get into because you guys need to be able to think that question through. So let's go ahead. We'll start with force, and I'll just go over a little bit of force and then an example, and then we'll end for the day. Okay, so that ends our discussion on energy. So force, right? So we all know, why isn't this, there we go. We all know that force is hopefully, I mean, my son's learning it and he's in second grade. So hopefully you guys remember a little bit of this. That force is just a push or a pull, right? It's something. We can't always really define what it is. Like we don't really understand what causes the force of gravity. We're not 100% sure. We think it has something to do with mass, and there's some theories out there about the space-time acting like a big mat, like a big mat, and the mass kind of draws things into itself because it's sitting in this three-dimensional mat type of thing. There's all sorts of theories out there about it, but we're not 100% sure, right? So we just know it's something. It's something that's either pushing on something or pulling on it or pushing it away, right? Some of that's visible, like whenever I'm pushing the mouse, obviously I'm the force. My fingers causing a force to push the mouse. A spring, we understand that force. So force is just a push or a pull. It's also, we can find force, or we can understand it, or we can get to it by taking a derivative of our energy. Okay, so let's start by looking at this plot of potential energy. Okay, so this is S. S is a distance. Okay, so we're looking at the distance, and we've got U there. And so we have this plot here, and I'm going to just kind of draw this more or less the way I have it on my notes. Okay, so we have this plot. And we have these points. Okay, so we have A, B, C, D, and E. Okay. And so I can find the slope of any one of these points, right? I can find the slope at A, I can find the slope at B, C, D, and E. And the slope here slope is related to derivatives, right? We've talked about that. Okay. If I take the derivative at this point, I'm finding the slope right at that point, which in this case, we know we would get a slope of 0 here. Right? If I were to get the slope at this point, I don't know what it would be exactly, right? But I know that it would be a positive slope. Here, I know that I would get a negative slope, and so on. This would be 0 again, and this would be a positive slope. Okay, so I can tell based off of this plot here where my slope is positive, where my slope is negative, and where I got a slope of 0. Well, that slope is also, so let me write it out. Slope is equal to du over dt. It's about equal, really. I should do that. T. ds, sorry. We're not doing dt, we're doing ds. Where s is just position. S is x, y, even theta. Let's just put r. It's just position, right? S is a position. Well, if we do kind of an analysis of this, we have du over ds, where let's say where s is actually x. Let's replace it. So let's say if x is if s is x, so we'll replace the s with an x. So we're looking at the x position. If I do the units, so that's what these brackets mean, right? The units of du is going to be joules. The units of x is going to be meters, right? So we know that a joule is a kilogram times meter squared per second squared divided by a meter. So this meter and one of these guys is going to cancel out. And so I end up with units of kilogram times meter per second squared, which is a Newton. All right. So the derivative of the potential with respect to position is going to give me force. Okay. So all of those functions that I found earlier are going to give me force, the ones that I found in energy. So F is the negative du ds. I was trying to remember why it was negative, and I can't recall why it's negative. It's got to do with the work. We'll get to, I think we get to that when we talk about work. Because energy and work are related. Yeah, I think we talk about why that negative is there later on. So don't worry about the negative right now. We talk about it later, right? And of course, force is a push. I'll explicitly write it out, push or pull. We don't always know what the cause of that force is, where it comes from, but if we see it pushing or pulling something like in a gravitational field, then we know there's got to be a force there. Okay, so let's look at our potential energy mgy. All right, so what is our potential when we're close to the Earth? Some distance y away up from the ground. If I plug this in, right, that's our position, it's y, so the s gets replaced with a y. Right, mg are constants, so those will come out. So we got mg dy with respect to y. Right, and that just goes to 1. So F is equal to negative mg. That's our weight. Right, so that's one force. Okay, so m is the mass. G is 9.81. And this is our weight. So to rewrite this more properly, our weight is equal to negative mg. Right, so that comes from our potential energy. Okay. One note I need to emphasize this. Now, mass and weight are not the same thing. Okay, mass and weight are not the same thing. I think that's particularly confusing for our area because we have a lot of students who live both who are living or coming from Mexico, like maybe um, Piedras or Allende or those areas, um, or like in Del Rio. There, what's across from Del Rio? I always forget.
Cunha.
Acuna, yes, or Acuna and stuff. And so whenever they weigh the cheese and the meats and stuff over there, they're using kilograms, right? It's un kilo de queso. Um, so so I think we kind of get confused in our area a lot with this concept because over there, whenever they're weighing it, they're actually weighing the mass. And over here, we get pounds. Like I need a pound of T-bones or something. And so we get those two things confused in our minds because of that, I think. Mass and weight are not the same thing, right? Mass doesn't change if I go to a different planet. If I have a 5 kilogram block on Earth and I take it to the moon or to Mars or to some planet X somewhere else, it's still going to be 5 kilograms, right? The mass of it doesn't change. The only way for me to change the mass of that object is for me to chop a piece off of it, right? So I have to break the rock or the block or whatever it is. I have to break it, split it, and throw out the one piece, and then the mass changes. But it didn't really change. It just got taken off and thrown out, right? The other part of the mass is still out there. So really, that. Um, so I have to do something to the object physically to change the mass. I have to break it, or maybe I burn some of it off, or something like that. I melt it. Okay. The weight does change depending on its location. Even here on Earth, the weight can change slightly from place to place because of the density. If I have different density under my feet here in Eagle Pass than I do in, let's say, Idaho, then my weight might actually change a little bit between those 2 points because the density is going to affect the acceleration due to the gravity, right? On not a whole lot, but a little bit. Or if I take it to a different planet, the weight's going to change because I'm in a different gravitational field. So weight depends on gravitational field. Mass does not change due to location. Right? It's a measure of how much of something is made up of, right? How much of something is in an object, how much stuff. Gravity is a force. Or sorry, gravity is a force. Weight is a force. Mass is not. Weight is a vector. Force is a vector. Weight is a vector. Mass is a scalar. Right? This is a scalar. This is a vector. All right. So those are two separate things. They're related, right? By this equation, they're related by this equation we just found. I can find the weight based off the mass and the gravitational field it's in, but they are not the same thing. They're not equivalent things. Right. So I really feel like I need to cover that because I always get that mistake on like exams or other things where they'll plug in the mass instead of the weight, or they'll say, well, they'll plug in the mass instead of the weight, or vice versa. Um, please remember, weight and mass are not the same things. Mass is in kilograms, weight is in newtons. All right. let's do another one. We had spring constant or elastic potential energy, 1/2 kx squared. And we'll do the derivative with respect to x because of the x here. So that's going to be negative d over dx of 1/2 kx squared. Excuse me. Those are constants, so those come out. So we're going to have a negative a negative 1/2 k times the derivative with respect to x of x squared. And so f, and I should put of a spring, f of a spring is going to equal to negative 1/2 kx. All right. So we'll notice a couple things here. First, we have this negative, right? The negative is there to imply that the force acts in the opposite direction of the motion. I should say of compression or stretch, of compression or stretch. And I'll show you with a picture what that means. Okay. So if I've got this wall here, and there's the floor, right? That's how we tell people that it's a solid floor or solid wall on the other side, okay, with those little marks. And I've stretched it out. Okay, so I've stretched the spring out this way. All right, so if S is going this way, my force due to the spring is going to go in the opposite direction. I shouldn't draw that line there. This is not a distance. There. All right, so the force is going to go in the opposite direction. All right, so if I'm stretching that spring out, then it's pushing back. And you can feel that if you were to get a spring or a rubber band. I don't have anything here. I guess I can use a clip. This is spring.
It has a resistance.
Yeah, it has a resistance. So whenever I've got this here, right, I've got this and I'm pushing it down, I'm applying a force this way. And so the motion is downward. This part of this clip, the spring, is pushing back up in the opposite direction that I'm trying to push it down, right? So the change in direction is down, but I'm feeling a force on my finger going in the opposite direction, okay? So, and it's the same with the compression. That was compression. Same with the spring. If I take a spring and I'm pulling it this way with the tip of my finger, I'm going to feel that spring pull me back that direction, right? I think we've felt that before. So that's what that negative means. Okay, and then we have the K. Of course, we have K, which is again just the spring constant. And then X is just the distance compressed or stretched. Okay. Excuse me. So, yeah. So now let's look at the gravitational potential energy, negative GM M over R. And this time we've got it with respect to R here, right? So that's what we're going to use down here. Plug that in, d over dr, negative GMM over R. Okay, so again, G, M, and M are all constants, so I can pull those out, and that negative can come out too, so I'm going to end up with a GMM times D over R the derivative, what am I doing? With respect to R of 1 over R, right? And that's just R to the negative 1, right? R to the negative 1 is going to give me a negative GMM over R squared, right? And hopefully you recognize this little bit here. We've seen it before. This gives us G, right? We saw that back in when we were looking at the energy. That's how we got the MGY. On Earth, right? That's true on Earth. But this gives us this equation though. This equation itself, not considering that, I'm going to delete that, just so that you guys recognize we've seen that before. But this is Newton's law of gravity. Okay, this equation here is Newton's law of gravity. And it just says that that's the force between two bodies, right? Some distance away from each other due to gravity, due to that mysterious thing we call that gravity. Excuse me. Whew. All right. I'm going to stop here. We only got 5 minutes. I don't want to have to stop midway between an example problem. So we'll continue with this on Monday. I'm actually going to upload a worksheet that we'll need for Monday. And it just goes over free body diagrams. So when we deal with force, free body diagrams are very, very, very important. And so we'll look how I'll show you how to do those. Hopefully you have some idea how to do that, but if you don't, that's okay. We'll cover it on Monday. Right. Have a great weekend. I did upload, since we have a little bit of time, I did upload an updated schedule, I think it was for this class. Yeah, so let me show that. Okay, I did upload an updated schedule here. So today we started talking about force, and we'll continue that on Monday and Wednesday. So just to let you know, so our exam 1 now, I think it was supposed to be on either Monday or Wednesday. I don't remember what the original date was, but now it's going to be next Friday. All right. So be ready for that one. We're supposed to use honor lock. I just asked this morning if that was available to us yet. So far, they haven't. They said they would contact the person in charge of that, and hopefully that's done by next Friday. If not, I don't know how I'm going to deal with this, but we'll see what happens. Okay. Another thing I do. I do think that we'll be able to go. I was just thinking about it. We should be able to still get to the thermodynamic stuff, it looks like. What I did is I tried to cutting out a day of the circular motion. we'll see how that works out. If it doesn't work out, oh well. Because I would really like to get to this stuff if possible. If not, we don't. But I really would like to. So we'll see what happens. If we have to go that other extra day, then that pushes this down to a review day. I really don't want to get rid of that review day because it's going to be a comprehensive final exam. So I want to make sure I at least go over everything, a little bit over all of this stuff, and tell you what's going to be on the exam on that review day. I usually don't do the review days because we don't have time, but for this one, I really want to have that review day. Okay. All right. So that's it. I'm done talking. Are there any questions?
Sir,
Yeah.
for the energy homework, I wasn't hearing like I was like a minute late. I didn't hear like how are we supposed to turn that in?
It should be submitted online normal. Did I mess something up? And I've got another question.
On the page, I can't see the submit button.
Okay, I messed that up. Let me edit it. There was something else that someone pointed out right here. This was supposed to say the 5th. Don't, if it says that, if I forget or I make a mistake on that, go by the date that's on here. Oh, you guys can't see it. And I have another question. I'll get right to it, Preston. Hold on. Don't go by this date. If this time you hadn't started it and you need the extra time, fine. But don't go by the date on here. I'll try to remember to go back and double check that. Go by the date that it's actually due when you see it down here, February 5th. Okay, and then here, let me put the submit button online. I'll upload. There you go.
Thank you, sir.
All right.
Sir,
Yes.
have you graded the first two assignments?
No, I'll be doing that. If I don't get it to do today, then I'll do that Monday or Tuesday next week. I know I need to get that done. I've been dealing with trying to catch up with the 2304 class. They made a lot of changes to that book, and I had an issue just the other day for those of you who were in there, where it wasn't opening. It was locked out. I don't know. It's a lot of stuff. They made a bunch of changes, and I'm trying to catch up with that right now. But I will get it done, if maybe even over the weekend, because it doesn't take me that long. And then will the exam be available until midnight on Friday? Yes, it'll be available all day, but you'll have a certain time that once you start it, you have to finish it within a certain time. But it will be available all the way till midnight on Friday, the whole day.
And you said you were unsure if we're going to have to use the lockdown or the secure browser, right?
Yeah, because they haven't said anything. They haven't got it set up yet. So we'll see what happens. I'll let you know more information whenever I get it. No, test is not multiple choice. I don't do multiple choice tests usually. Yeah. All right. Okay. I'll see you guys on Monday. I'll see everybody on Monday. You guys have a very safe weekend.
I just had one more question for you, Mr. Irwell.
Go.
On our exam, are we allowed to bring equations or?
Yeah.
Okay.
I let you. I usually give it to you, but you guys can do your own sheets this time.
Okay, because I don't know how that works with the lockdown browser with it flagging and everything.
Yeah. Me neither. it's brand new. All right, it's a new thing, so we'll see. And they're not giving us enough time to play with it. So I'm, we'll see how it works.
We are the test subjects.
You are, and I'm sorry. You are, but I wish they'd get on that, because they asked us 3 or 4 weeks ago if we wanted to use it. I mean, that's plenty of time, in my opinion, to get things going, but they haven't gotten it going yet. So we'll see. I'll let you guys know more as I know more. Okay.
Thank you, sir.
All right.
Thank you, sir.
Bye.
Thank you.
Bye, sir.
Bye.